Hanbaek Lyu from University of Wisconsin will tell us about scaling limits of soliton statistics in the randomized box ball systems.
Okay, thank you very much for organizers for the invitation. I'm really happy to be here. It's first international workshop on box ball systems. I was a PhD student and I visited Lionel Levine. He's a probabilist at Cornell University. And during our visit, he suggested there's a box system called box ball system. You want to analyze it together with while you're here. And then we started working on it. And that's our 2017 or 2018 first paper. And ever since then, I started working on like more general version of it with a lot of great collaborators. I hope to meet you, a lot of new collaborators here in this workshop. Okay, so we probably had a lot of this same kind of style of introduction of the system. So I'm glad that I can skip this and then tell you more about the more interesting stuff. So the history, all the nice connections with the solitary waves and all the nice physical systems. So there's much better experts in these more classical topics. So we want to capture some continuous solitary waves using discrete box and ball model. There's a lot of ultra-discrete limit. So let me give you a brief recap of the system. So I'm going to use this representation of the dynamics most of the talk. So you have a binary configuration of zeros and ones are balls and zeros are empty boxes. And time evolution by using carrier is pretty simple. You're going to pick up, I'm not sure why the slides are going up and down. Yeah. So the carriers keep picking up the balls like this. I really had a hard time making the smooth animation, but now the entire slide going up. Okay,
I think the screen might be too big.
Is it? Oh, okay. I wanted to show you bigger picture. Okay, there's a compromise. All right, so that's how it works. Okay, and as you can see, you can keep repeating the system, and then you will eventually get a lot of solitons coming out, and the fast one will come to the like a travel faster speed. So at some point, there's no interaction between the solitons. Of course, there's a lot of different related areas, and you can have a different limiting procedures to get the box ball system from all different angles and all different branches. I'm good that I'm finished the intro. Okay, so randomized box ball system is, there's a lot of different ways to randomize it. And the version of randomization I'm thinking of is very simple one, where you keep the dynamics exactly the same, but you start with a random configuration. Okay, and then the soliton lengths, number of solitons, all the statistics you can think of are random variables. So what can we talk about? What can we say about these random variables? How do they scale? What is a limiting behavior? What is a expectation? What is a fluctuation? We can ask a lot of different questions about it. This is the main question that I've been studying. So if you have one-sided randomly initialized box ball system, then you can think about the final soliton statistics is a Young diagram. It's an invariant Young diagram. And you can ask what is the limiting shape of the Young diagram. It's related to the question we had before. And Makiko talked a lot about this getting invariant measures of this bi-infinite extension of the systems. There's a lot of papers in it. This is a very old review of the literature, probably made it like a couple of years ago, and there has been so many papers since then. So there's many more works and that I'm not covering in this slide. Okay, so I want to get you to the probabilistic aspects and the phase transition of the soliton behavior. Okay, so this is a summary of the model and the summary of the results. So the system has size n, and it means we only try to occupy the first n boxes, and afterwards all the boxes are empty. Okay, and then you simply put a ball independently with the probability p for each box. So we are doing kind of binomial NP initialization, and then you keep running the system. Okay, so and you will decompose into solitons. And you can think of a Young diagram by encoding the lengths of solitons. So the first column of the Young diagram is going to be longest soliton length. Second column is the second soliton length, and so on. Okay, so you have a binary string, run the dynamics, collect everything by a Young diagram. Okay, you're asking, we are putting random measure on the initial configuration. You are pushing it forward by the box ball system dynamics, and you want to know what is the induced distribution measure on this Young diagram. So that's a basic question. And depending on the system size, so the soliton lengths and number of solitons can grow in N. So how does it grow? So that's the main question. So the main, for this elementary box-ball system is if you look at this first column here, so it says the number of solitons. So you can think of the column, if you think about, so the columns are corresponding to solitons. So if you look at the length of the first row, that's exactly the number of solitons coming out of your system. Okay. So how does the number of solitons scale with respect to this parameter P? Well, there's a slight constant difference, but it's always linear. Okay, it means regardless of your parameter P, you will always observe linear number of solitons. But for the columns, there's a nice phase transition depending on the parameter P. So there's subcritical regime, critical regime, and then supercritical regime. So in the subcritical case, this is when you have more boxes than more balls. And in that case, your first longest soliton, your longest soliton has order length order n, it's pretty small. And all the other subsequent solitons have the same order, only constant difference. And in the critical case, you have square root of n scaling for the largest soliton. And also you have the same length scaling for the subsequent solitons. And in the supercritical case, your longest one is linear length, and then all the subsequent ones are order log n. So this is very reminiscent of the phase transition of the Reshetikhin random graph. And so it's kind of this lambda 1 is kind of a giant component emerging from the random graph situation. It's very similar to that. Okay, so let me quickly describe where is this phase transition coming from. So once you see this picture, it's very natural to expect. So a lot of speakers talked about path encodings of the system. So here's one way to do that. So whenever you see 1, you're drawing a lattice path as you read the configuration. So if you see a 1, then you go up. If you see 0, and if you're positive height, then you go down. Okay. If you're already at 0, then you cannot go more negative. You stay at 0. Okay. So this is you can build up this black lattice path by reading this first configuration. The second row, this is after one round of the iteration. And then you can also construct similar lattice paths for the second configuration. I'm showing it in green. Okay. So, so the first one is actually encoding the number of balls loaded in the carrier at each point. Okay. And then, so if you think about the evolution from the black path and the green path, this is evolving the carrier load path from one time step to the other time step. So this is very related to the Pitman's reflection transform. And right, so how do we read off? How can we read off the Young diagram by looking at the initial configuration? So one obvious way is just run the dynamics and then see the soliton, right? That's one way. But you're putting this nice independent measure on the initial configuration. So if you had to wait a very long time, there's always going to be this correlation building up through the dynamics. But if you have some way to read off the solitons from the very first independent measure, then you can do a lot of good analysis on it. And we already have a good correspondence, like a 0-1 arc law. But here's a path version of it. So it's our interpretation. So you build up this lattice path by reading the soliton configuration. And we're going to chop off this upstroke and downstroke. So we're going to chop off the peak. And each chopped off peak is going to be one cell in your first row of the Young diagram. So we chop up, there's 6 peaks, and then your first row is going to be 6 cells. And then there's going to be what we call as heels. It's an upstroke, a bunch of horizontal strokes, and then downstroke. Okay, so there are 2 heels. We chop it off, and then there are 2 cells in the second row. There's only one left, Okay, that's a Young diagram we build, and that's actually, this Young diagram has actually time invariant. So this is exactly the same as 0-1 arc law, but interpreted as in a path space. So if you construct the Young diagram this way, at any given time configuration, it's invariant under time. So that means you're given a configuration, construct this Young diagram this way, or you evolve this configuration one iteration, construct a path, and then construct the Young diagram that's exactly the same. Everything's commuting each other. So in particular, you can construct this Young diagram from the initial configuration, so where everything is independent. Okay. So that's where a lot of good things can be analyzed. And one direct consequence of this lemma is, so what is the length of the column, first column, right? So it corresponds to the number of times you apply this hill-flattening operator, right? So that means that's exactly the number of maximum height of the original lattice path, okay? And that's invariant. And we said this first length is the column length is the longest soliton length. So what we can get out of this is the maximum height of this lattice path is exactly lambda 1. We can associate the behavior of lambda 1 to the maximum of this kind of random walk path on the lattice. Okay, so simple picture. And another nice heuristic we can get is, so the number of solitons is actually the first application of hill-flattening. So it's exactly number of upstroke and downstroke. That corresponds to the number of 1, 0 string in the original configuration. So if you just do a heuristic calculation, the density of seeing 1, 0 string in your environment is p times 1 minus p. Okay, so you can expect to see linearly many solitons in that way. So a more precise statement of the row-wise scaling is given like this. So if I take any row, ith row of the Young diagram, and divide by n, okay, and the ratio is going to converge to some number, and that number is actually the probability of your random walk path doing an excursion of height I. Okay, so we are basically counting the expected number of sub-excursions of height I, and that's exactly going to be the ratio of the row length divided by n. And you can do also some CLT for this first row, ith row. And our original proof, back then, we didn't know this fancy connection with combinatorial R and all this more advanced stuff. So I did my brute force moment computation, and it was quite complicated derivation for this one. But there's a much cleaner way, a better way, more powerful way to use combinatorial R and thinking about running finite capacity carriers, and it's a more well-developed theory. So I'm going to talk about that as well. Okay, so we can do a row-wise scaling of the Young diagram. We are not touching the column, but because we know the rows are all going to be linear. So if you divide the row length by n, the Young diagram is gonna converge to some limiting shape. So we can plot the limiting curve, and we get exact formula for this by solving this excursion probability. So that's a one-sided scaling limit. Okay, what about the columns? So we mentioned we are building up a lattice path, and then the first column is the maximum height. Okay, so depending on the density P, your lattice path, we're calling it Harris walk. But it's really a simple random walk on the lattice. It's censored at 0. Okay, so the positive probability of the probability going up is P, probability going down is 1 minus P. So you compare that. If P is less than half, then you have a negative drift. Okay, so your excursion is having a negative drift, so you cannot really make a big excursion. Okay, so there's gonna be linearly many excursions, and each excursion will have an exponentially small height. So it's basically a maximum among order n many independent exponential random variables. So take the extreme statistics, and then you're gonna get this log n, and we can do more fine analysis, and then find the distribution is very close to Gumbel distribution. It's a subcritical case. And the supercritical case, the probability of going up and down are exactly the same. So if you think about this lattice path, this is almost like a reflecting simple random, one by a simple random. Okay, so so each excursion is a Brownian simple random walk breach. So, and then you spend a geometric time until you see the first ball to the next. But this geometric waiting time is gone in the Brownian scaling. So you can do a Brownian rescaling over here. And then you can write down the lambda 1 first soliton length at the maximum of the reflecting Brownian motion in this case. So that's the exact description of lambda 1 in this case. And in the supercritical case, it's a random walk with positive drift. So after some finite time, the random walk will just keep increasing, and you can compute the drift, and the first soliton length is going to be linear with exactly this constant. Okay, So pretty simple picture for phase transition. You're tracking the load of the infinite capacity carrier, and depending on the ball density, it either has positive drift, negative drift, or is critical. So depending on it, you can basically analyze the random walk path and then transfer that to some statements of. So we talked about lambda 1, but if you're interested in lambda 2, how do we do lambda 2? Okay, so lambda 1 was the maximum height, but lambda 2 was like a second height, maximum height. Well, it's not exactly as simple as that, but it's something close. Okay, so I'm gonna introduce this operator that is acting on the lattice paths. We're calling it excursion operator. Okay, so it's very similar to the Pitman's reflection operator. So you're subtracting off the running minimum, but the point where you do this running minimum is at a maximum, rightmost maximum. Okay, so let me give you a picture on like how to do this. So this interpretation is actually from Pitman himself. So Lionel had some memory of this operator, and he asked Pitman, have you seen this one before? And he shared his slides about 10 years ago, and then there was this operator defined. He defined this operator to study continuum trees for Brownian motions. Okay, so this is his interpretation. You flip the path upside down, fill it with water, okay? So all the way up to top, and then put a hole in the rightmost minimum. It used to be rightmost maximum, okay? And then you drain out all water, okay, from this hole, right? Can you see that? Let the water drain out through this hole, okay? And these buckets will still contain the water. And then flip it back, and then just record the height of the remaining water, okay? So that's the operation. That's the excursion operator. We had a talk, Pablo Ferrari also explained this. So he had like a tree version of it, right? So you take the rightmost, longest path and then do some sub-branch like exploration. It's exactly the same process. So if you think about merging this lattice path horizontally to make a tree, then this uncolored part of the lattice path corresponds to the longest branch of the tree. And then the remaining ones are giving you the extra bushes and other branches. Okay, so exactly the same operator. But the nice thing about this excursion operator is that it's a Lipschitz operator, so it has like nice properties. So you can commute with a lot of different operations. So it's a good way to extract the column lengths. So the lemma here is, if you want to get the jth column length of the Young diagram, what you need to do is you just apply this excursion operator j-1 times and take the maximum. That's going to be your jth solve. So this is what we use to analyze subsequent soliton. Any question up to this point? Yeah, for the multicolor case, and then yeah. Okay, so let's go to the multicolor case. I mean, so distribution of lambda 1 is almost I described, and the fluctuation for a subcritical case is Gumbel distribution, and the critical case it's a maximum reflecting Brownian motion, and the supercritical case it's linear. And what the more interesting thing I wanted is to get some kind of like global scaling limit of the Young diagram, but unfortunately it's not the case for the box ball. So we have the row length is always linear, but the column lengths can be linear or square root of n or log n, right? So it never matches up with the area. So if you just multiply the scaling together, it doesn't work very well. So it seems like we need to look into some middle part of the Young diagram, not the extreme first few rows and first few columns. They are kind of extreme behaviors. So if you really wanted to get some scaling limit, like the Plancher measure for the Young diagrams, we need some like intermediate soliton length analysis. But yeah, so I'm not getting there right now. Okay, so we had some nice combinatorial operations to extract all the columns, all the rows, and then we can push the IID measure onto the soliton lengths and Young diagrams and get all the analysis done. But what do we do for the multicolor case? So a lot of speakers also mentioned about this. And here's our interpretation of how the carrier works. Probably a lot of you have already known this. So now the balls have colors from 1 to kappa. Kappa is a parameter. And the carrier is still moving through the environment. Okay. So it will pick up all the balls no matter what. Okay, that's still the same, but the color of the ball that pops out of the carrier is now depending on what's inside. And the rule here is actually combinatorial R, but a more transparent, I guess, easier interpretation that we have is it's a kind of a circular exclusion happening. Okay, so you have 3 here, and then 1 comes in, and then if 2 comes in, 2 is going to be inserted into the carrier, and it's going to exclude the largest smaller color in the cyclic order. Okay, so 1 is the largest smaller than 2 in the cyclic order, so 1 is gonna go out. Okay, and if there's an empty box, you still you put down the largest color. 5 comes in, and 5 will exclude 2, and 1 comes in, 1 cannot exclude 5. 3 comes in, 3 will exclude 1. So you're kind of arranging your colors in a cyclic space, and whenever there's a new color, you look at the closest counterclockwise neighbor, and then you exclude that one. Okay, so that's how combinatorial R works in this particular case, and it's also kind of a periodic version of row insertion, Shense row. And then you can keep evolving your system like this, and eventually you will have a decomposition into multiple colored solitons. And yeah, the carrier process works as a circular exclusion, and it's actually combinatorial R. Yeah, I just mentioned. So in this case, you can also associate with the limiting Young diagram. So as I mentioned, there's a higher order Young diagrams here in this case, but if you still want to know the number of solitons and the length of solitons, you can just record. There's the longest one has length 4, the second one is length 3, and so on. Okay, so the question, yeah, you can still relate associate a Young diagram. So now we can do a similar IID configuration and see what is a push forward measure on the Young diagram. Okay, so you have system size n, put IID both configurations with color density given from P0 to P kappa, and P0 is the empty spot. And you fix these parameters and then let n go to infinity, and you ask what is the scaling limit of this Young diagram, just like we did before. As before, row length is always linear order, but the column lengths, there's a nice phase transition, a more complicated phase transition than in the 1 color case. So before I go there, I just added the slide because there was a related question in the previous talk. Okay, so this is from our joint work with Acho. If your initial configuration is not IID, but if you condition on being highest state, it means there's the monotonicity of a color ball counts. If you color the number, if you count the number of balls, basically the carrier path process should live in a vial chamber. There's a nice monotonicity of the colors happening. Okay. In that case, you can actually exactly compute the measure on the whole tuple of Young diagrams. And the proof of this is pretty simple, but it's building up on this huge KKR machinery. And you can exactly write down, it's kind of also looks like a Gibbs measure on the Young diagram, but you have this additional factor depending on various statistics of the Young diagram. So one way to analyze the scaling limit as Young diagram is to directly attack this formula, like many of us do in integral probability. You have a determinantal formula, take various scaling limits, and that's going to give you some nice like KPZ style scaling and all the good things. So we do have a closed form solution, a closed form measure expression. So technically we can take all those limits, but it's really, really complicated. And Acho is really expert in doing it. And he does this using Thermodynamic Bethe Ansatz. Probably he's going to talk about it in his second talk. But in this talk, I'll do a more probabilistic approach. So that's what we have as a backup. Okay, so the first result is a refined result for the column lengths. Okay, so in the multicolor case, row lengths, sorry. In the multicolor case, so we still have a linear scaling of the low ranks. So what is a ratio? What is a limiting ratio between if you scale it by one over the system size? Okay, so if you take the ith row, this superscript A is the order of the Young diagram. In the multicolor case, there's a kappa tuple of Young diagrams. But yeah, if you think of, you can just think about A to be 1, then it's the number of lengths number of solitons of length at least I. So the limiting ratio is expressed in terms of this factored Schur polynomials, depending on the size and the order. So yeah, this was a very nice formula. I had no idea how to compute it, but we had some expression on the stationary measure of the finite capacity Markov chain, and there also did some like magical computation and some relations, and it's coming out. Yeah, so it's a really nice expression. So I'm not going to talk about too much about this low ranks. The more interesting part is the column length. Not more interesting, but more, I guess, more challenging for me is to figure out the exact column lengths. Okay. So for the column lengths, you're still running the infinite capacity carrier. So it's still doing the circular exclusion. And you can think about everything here is on a ring, color space. And if a new color comes in, it will exclude the largest, smaller color. Okay. So if 2 comes in, then you can think of 2 is excluding color 0. So that's why 0 is popping out. Okay. And then 5 comes in, and 5 will exclude 2 in this case. So that's how the carrier process evolves. Okay. And then we're going to think about it as a Markov chain. So you keep track of how many balls of each color is in your carrier. Okay. If you insert 1 ball and then there's some change in the carrier, so you can have a state space. In this case, there's 2 colors. So, so the carrier process is moving on the positive orthant of the integer lattice. And depending on where you are in the state space, the transition probabilities are given like this. Okay. For example, here you have both positive number of color 1 balls and positive number of color 2 balls. If there's a color 0 encountered, then that will kick out color 2 balls. So the number of color 2 is decreased by 1. The number of color 1 ball is still the same. So that's why you go this right direction. But if you encounter color 1 ball, color 2 ball, that will exclude color 2 ball, color 1 ball. Okay. So we have a decrease in the first axis and an increase in the first axis. So that's why the Markov chain moves in this way. So it's a kind of 2-dimensional random walk, but you can also move it diagonal way. And also the way the transition on the boundary behavior is a bit different. Okay. So on this line, it means there's no color 2 ball. So if you encounter empty box, then your color 1 ball is gonna decrease by 1. And if you have a color 2, that's still the same. And if you have a color 1, then you're gonna increase by that. Okay. So you can think of the carrier process is moving in this space like this. It's a Markov chain. And here's a simulation on this carrier of this multicolor carrier process. So there's 4 colors, and I gave these kind of densities. They're very small density for empty box, and there's 2 largest density for color 1 and color 2, and color 3, and color 2 density is a bit smaller. Okay, and I'm plotting the number of balls in each color. So there's a supercritical linear behavior in the color 3 balls, and there's a subcritical behavior in the color 2 balls, and there's a critical behavior on color 1 ball. Okay, so depending on the parameter regime, all different subcritical, critical, supercritical behavior is all encoded in the same carrier process. So that's one challenging aspect of this multicolor case. This is like a doubly critical. So all the colors are critical in this case. So it seems like each color count is doing its own reflecting Brownian motion, but of course they are evolving according to the one source of randomness. So they're all intertwined together. Okay. So analyzing this multicolor system is a bit more challenging. So, so here's a lemma or observation we're using. It's still about the same. So where is the phase transition? So it was non-trivial to figure out, but it turns out that the answer is you compare the density of the empty box and you compare it to the density of the largest density of color. Okay. So if you have more empty boxes than the largest density, that's a subcritical case. So in this case, you can actually compute the stationary distribution of this Markov chain. And it's actually very nice. It's product of a geometric distribution. It's proportional to the ratio between the color eyeball divided by empty box density. And there's some normalization constant. And you can think of an excursion in this high dimensional version. Okay, starting from 0, 0, you do some excursion, and then you're going to come back to 0, 0 anyways, because it's stationary, so you have some negative zeros. So still, we are looking for the maximum height of the excursion. So you'll have multiple high dimensional excursions like this. And then if you look at the maximum excursion, that's exactly lambda 1. Okay, so we still need to analyze if you have a single multicolor dimensional excursion, what is the maximum height you achieve? Okay, and more precisely, it's gonna have an exponential tail, but we need to get the exact exponent to get the exact soliton. And this turned out to be pretty difficult problem. It's a high dimensional gambler's ruin problem in probability. So usually you start with $1 and then you do the game until you win $100, or if you go to $0, then you go home, right? So you ask, what is the probability that you reach $100 before reaching 0? So that's a classical one-dimensional gambler's ruin. But now we have a multicolor case. So you start with or 1, 0, 0, 0, or all 0. And then you want to reach total n balls. Okay, that's your target before you drop out all the balls. Okay, and what is the probability that you achieve total n balls before you're going back to 0? Yeah, I've been stuck at this problem for a very long time. Recently, a couple days ago, I made some progress here. I was very motivated. I need to present something new for this workshop. So yeah, really tried hard. Okay, so once you get the scaling, exponential scaling for this excursion height, automatically you can get this lambda 1 is going to scale like theta log n. And theta is exponent. So can we really get this theta? So here's what we found. So I'm going to define some functional on this space. So if you compare this to the stationary distribution, we are flipping upside down. So the stationary distribution was proportional to the product of pi over p0. But now the functional is p0 over pi. So it's pretty natural function. And I want it to be martingale. You can do the combinatorics here, and it turns out it's almost a martingale. So if you look at this functional after one time evolution, conditional on everything else, the previous iteration, then it's the previous value times the sum of the probabilities. Okay, and if it is a martingale, if the sum is always 1, then it's a martingale, and you can get the gambler's ruin probability exactly. If it's a less than 1 or equal, bigger than 1, depending on the side, you're getting upper bound or lower bound on the ruin probability. So what is the sum? So you're summing up all these probabilities, and this index you're summing up is I prime, and I prime is the color of the ball that's popping out. Okay, so you had a carrier gamma t, and you're inserting a ball color I, and then I prime is the color of the ball that pops out. Okay, so if every color is represented exactly once, then you're just summing up all the probabilities, so this is exactly once. And that's exactly what's happening in the interior. So if your Markov chain is in the interior, then it's a cyclic exclusion. So if you insert color I, that will always pop out color I minus 1, mod kappa plus 1. So this sum is exactly 1. So this behaves like a martingale if you're in the interior, right? But as soon as you hit some boundary, it can be a sub-martingale or a super martingale. Because if you lack some color, so some color is not going to be represented. So depending on the relative orderings of these ball colors, it can be bigger than 1, smaller than 1. So, but there's some coupling argument I can do, and then you can use the stationary measure formula. So it turns out the exponent we want is actually theta. The theta we want is actually the ratio between p star and over p0. So that's a nice generalization of the one-dimensional case. And as you remember, maybe, so the criticality is coming from comparing p0 and the maximum p. And the ratio between them is actually giving us the same thing. So we can get the scaling of the lambda 1 to be this constant. So these are summary of the results of all the scaling. So I mentioned we have linear scaling for the rows, and we have exact ratio expressed in terms of the shear polynomial. And lambda 1, the largest soliton length, is having the same phase transition. And we had to do some multi-dimensional gambler's ring to figure out this constant in front. But there's one more phase transition in the subsequent soliton lengths. So because a lot of different type of Kerov process can be nested within one Kerov process, actually there's a regime where your subsequent soliton lengths in the supercritical case are still length order square root of n. So in the one color case, if there's a linear soliton, all the other was a kind of dust. It was a log n. But it's possible to have linear length of soliton, but all the follow-up solitons are order square root of n. Okay, when does it happen? That's when there are multiple densities that has the largest value. Okay, so there was a case in the simulation I showed you. In this case, P star is 0.35. This is the maximum ball density among the positive colors, and there are actually two of them. Okay, so they're competing with each other, and the competition also generates like a critical length solitons. That's what's happening. Otherwise, if there's only one unique maximizer of this positive ball density, then the picture is exactly the same as this. Okay. And these are more precise statements. So we can get the J soliton lengths are exactly of this form. We didn't know theta before, but now we know it's theta P star over P0. And there's some nice expression like this. So technically, you should be able to get the scaling from this joint measure expression using KKR bijection, and also had some computation about it in our previous paper. But I wanted to know, like, is it possible to get the scaling using probabilistic argument? And also the computation there, I believe, was for a particular case where there's a geometric a ratio between all the densities. And that's scaling for the lambda 1. Okay, so let me summarize the approach that I described in this talk. So we have a box-ball system. It can be single color, multicolor. It can be more exotic. And we want to initialize it at system size n according to some IID measure depending on some parameters. Okay, and then one way to get the Young diagram is just running the dynamics. But there's, due to this integrability of the system, I should be careful in saying integrable. There's a lot of different nice ways to extract the soliton lengths. So you can think about running finite capacity and think about a Markov chain and doing some law of large numbers type analysis. Or you also saw lambda 1 is kind of extreme statistics of all these excursion heights. Yeah. So the rows are actually, in short, it's additive function of some underlying irreducible Markov chains. So you do the Kerov process is going to give you some finite state Markov chain if it's finite capacity, or infinite state Markov chain if it's infinite capacity, and do some analysis on it, get some stationary distribution, analyze some mixing or ring probabilities, and that's going to tell you everything about the rows. And if you directly want to get the columns, it's coming from the extreme statistics of the same Markov chain. So these two different regimes are described in kind of different sides of the same process. So I think that's maybe the source of this scaling doesn't match up in the exact way. So as opposed to that, if you have uniform random permutation, if you do RSK, then it's symmetric under this flip operation. So there's no distinction between the row side and the column side. But here it seems to be based on different mechanism. Okay, any question to this point? Okay, so in the remaining like 5 minutes maybe, I want to kind of do a more entertaining slides. So I have variants of a box-ball system. We had a lot of interesting variants of box-ball system in this workshop, and they're all coming from some serious integrability limits. But these systems are just it's my curiosity. I just made up and then coded up and saw how it behaves. But I had some intuitions behind it, so let me explain some of them. So my first motivation is to have a spatial version of box-ball system. Okay, so far our box-ball system is one dimension, right? Our waves, we want to model the solitary waves, but we're kind of always looking at a section of the wave. So can we have a more spatial wave coming like this, right? So can we add a spatial dimension to the box-ball system? Okay. So here's one version. So now your space, it's not a one dimension, but it's two dimension. And So it used to be a 1 plus 1 dimension, right? There's a space in one dimension, time in another dimension, but now it's 1 plus 1 plus 1. So yeah. And the way it evolves, I didn't write it down here. Each row is exactly the same. So you run the carrier in each row, and then you're gonna pick up, the yellow is a ball. You're gonna pick up the ball and then drop it in the empty box. Okay, that's exactly the same. And the number of balls are not changing within row by row. Okay, but the interaction comes in by doing additional exclusion along the spatial direction. So if you pick up a ball, maybe can I write something? If you pick this up, usually you will put down at this location. Okay, but there's a neighboring site where it has a ball. Okay, so this node of the graph has a ball. So you're gonna skip this guy and then put it over here. Okay, so there's an additional exclusion happening in the spatial direction. So if I revolve it one step, it looks like this. Another step looks like this. So every line is doing a box ball, but there's a weak interaction between the rows using spatial exclusion. Okay, so that's how it evolves. So we used to see every line as a soliton, but now there's like a aggregation of the solitons in different space point, and you do see some like cluster of solitons emerging in this picture. Okay, and then so this was ball density 0.4, and there's a ball density 0.5 case. There's the first iteration, and do it. So you can see the size of the soliton cluster is kind of bigger in this, and then I can increase the soliton the density a bit more, and then now it almost formed a gigantic wave in one piece, but unfortunately it breaks down at the end. Here, it's not exactly one piece, so you can increase the density even more, and now it's like a one single wave, and even more the one single wave. So it seems like there is another phase transition in this system. So the 0.5 phase transition that I described to you for the usual elementary Takahashi-Satsuma case is still the same. So we can show you do the carrier pass, and there's a phase transition line by line, row by row at 0.5. Okay, so if your density is bigger than 0.5, then you expect to have a linear length of soliton each line. Okay, but there's a new dimension added, and you want to know whether these linear solitons can stick together and then make a big two-dimensional solitary waves. So it seems like there's a like upper critical, like a super critical density above which all these solitary spaceships are like glued together. Yeah. Okay. So that's still a conjecture. And there's another version. So here is a faulty version of the usual BBS. Okay, so same thing, but now the carrier has an epsilon probability of doing something wrong. So something wrong means it had to pick up a ball, but it skips it, or it had to drop a ball, it skips it. Okay, there's an epsilon probability, and so this is an example. You have longer soliton beneath, behind, and the shorter soliton behind. So usually there's a scattering, and then they swap each other, and then just go through. But now there's a small probability that a ball is skipped. So in this case, this ball was skipped to be picked up. So now it becomes a dust, speed 1. And then this is a longer simulation on the same system. So there's a occasional dust coming up, and they'll fall off of the big soliton. So here's a bigger simulation. And this is simulation starting from one gigantic soliton of length 100. And this upper envelope is the soliton you started with. And it's facing some friction, and it's keeping falling apart at some rate. So we can compute the exact curve here. And all the remaining dust are just falling like a rain here. But there's some curious interactions still going on here. So what's happening in this case? Yeah. So everything is either moving at speed 1 or speed 2 in this case. So if you run a soliton, it will eventually fall apart into dust, and everything will come out as speed 1 or speed 2 particles. And this is, you subtract speed 1 so that everything is either dropping or slightly moving to the right. Okay, so this is the last picture. So this is the evolution of 101. So you have ball, empty, and a ball. If you pick this up and put down here, and then if you skip it, then it's possible that they stick together. And there's epsilon probability of doing something wrong. So that means there's a large probability that this will behave like a soliton of length 2. Okay. So whenever these two balls stick together, they will have speed 2. That's what's happening in this line. So they travel together as speed 2 soliton, but with epsilon probability, they can break up. So either you don't pick this first thing up, or you mess up with dropping this one right away. So then you have an empty space between them. So they behave like a speed 1 soliton. So we subtract it off by 1, so things become just vertical. So, and there's a fluctuation. This is symmetric random walk. So actually, if you think about the gap between these two balls, it actually behaves like a critical character. So I think that's what's making up this final state of the behavior in this erratic system. What was interesting in Otto's talk was we are fixing the probability epsilon to be to fail something, but in that case, the probability seems to be depending on the load of the carrier. So if your carrier has more balls, then it behaves more like a deterministic carrier. But if it doesn't load that much, then maybe it's more erratic. So in this case, maybe is it more integrable in some sense, or can we do more analysis in the case? So that's a lot of interesting questions. Okay, some other questions, but yeah, I guess I'll finish my talk at the point. Okay, thank you.
Thank you very much for the talk. Are there any questions?
You said in the last model, this curve, you have some way to describe this curve?
Yeah.
So what is it's a real analytic function?
I did some computation. It was like almost done, and I was running out of time. Okay, so I'd say okay, it's doable. But basically, it's you get the rate of losing a ball and take the average, and yeah. So if you have soliton length n, then basically every part is lost with probability epsilon. So if it is longer, then you have more probability of losing more balls. So, and if it is short, then it's a less probability of losing balls. You can compute exact like a expected length of the soliton after one iteration, and then yeah, that's going to give you this curve of the expected length.
So you will not need to take into account the again combination also.
Yeah. So that's
again.
Right. So for the longest one, I think we're fine, because we are still this thing is the fastest. So all the dust will have speed 1 or speed 2. And it's possible to have speed 3 very briefly. Like if there's a like things like this, then there's a particular sequence of messing up to make it like a triple, and then you have a speed 3. But this is like a probably at least m was epsilon squared, so it's going to be very rare. So you can expect to have everything speed 1 or 2. So as long as your first soliton is still having a good length, so it's just applying some mean field model for the first soliton. But what's happening for the second one, it's more interesting. So something falls off from the second one, but it can start interacting. Something falls off the second one and start interacting dust that fell off from the first one. So there's more. Yeah.
Okay. Interesting.
I just have a curiosity. So in this model where you have weak vertical interaction, so does it make sense to ask what is the how does it affect the macroscopic hydrodynamics?
You mean the scaling of the solitons?
Yeah.
So I mean, I can say something about the system. It's still you can still show the maximum of the carrier height on each section is preserved. So it's not a carrier path. It's a carrier surface, right? So you're scanning the entire environment and then building up a two-dimensional surface, and the height on each section is preserved under the dynamics, and that's going to give you the length of the soliton on each section. But what it doesn't tell us is how do they aggregate together. So because of this spatial exclusion, if you have 1, 1, 1. So the first carrier scan is going to pick this up, but this ball is not dropped at here. Right? And so usual evolution is 1, 1 and 0, 1. So this has speed 1, this has speed 2, so they fall apart. But because you cannot really drop it at this point, you need to drop this at here. So you need to end up with this one. So like a faster one is kind of dragging the shorter one. So that's how they aggregate together locally. But I'm expecting some kind of percolation argument can be possible. So if your density is large enough, then there's like some percolation happening through the spatial dimension. So you get like a big soliton.
Or online? I don't know. I don't see anything now. I don't know. Do you see any questions online? No. Okay. Actually, just a quick question. Is there any integrability kind of, do you see any integrability in this two-dimensional model? Some kind of integrability?
For two-dimensional model, I'm not too sure. So the sign of integrability was the preservation of the maximum height of the carrier surface.
Yeah.
But for this erratic model, it actually came from vertex model. So you're applying vertex model. When Q equals 0, there's only one outcome. But if Q is very small but non-zero, then there's multiple outcomes. So we are thinking of it as a multiple realizations of the same trajectory.
I see.
So we can do Yang-Baxter, and there's preservation, everything. But there's some preservation of energy, but it's hard to interpret what is an energy. What does it mean?
And now it's a stochastic model.
Yeah,
right?
exactly.
So it's different, but maybe some integrability structure, algebraic structure.
Yeah.
Yeah. Okay.
So we get some invariants, but it's not clear what does an invariant tell us about this particular.
Yes, indeed. Yes. Okay. Thank you very much for the talk.